what? The first part of this, just like I did with the other class.
I'll catch it in my mouth.
I'm kidding. Okay.
Extra credit if he gets this in his mouth.
What's that?
Extra credit if he gets this in his mouth.
There's no way he's catching that.
There's no way you can get pretzel stick in Oh, that was good effort though. Very good effort.
It's a bit of an overthrow.
That was good. Really good effort there. Okay.
How'd you get that? Someone that broke. Oh.
Okay, am I correct that we have, how far have we gotten on the back of page 2? You tell me, I forget where we ended up with box 3 and A and 3B. Did we get ready for the bottom line in the box? Have we gotten down to that part right there?
Yeah.
Okay, good, 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 good. So, the bottom line, this is the big picture, what you're drawing from this so far at this point in time. We're going to add a little bit more to it so that we can use this to find areas today. But the idea is, and I'm just going to put this part right over here, even though I picture it on the overhead, but bottom line, I'm not going to do that just yet. Remember, the idea is we're trying to cut the shape, whatever it is. So I'm going to draw a little function over here that looks different than the parabola that we've been working with so far. Let's say this is our function, y equals f of x. And we're being tasked with trying to find the area from A to some other point B. Now, you've noticed, as of from yesterday at the very end, that when we do area, initially we talk about area above the x-axis and we get positive answers. Do you remember what happened when we did area below the x-axis? We got negative area. Didn't mean it didn't exist, it's just a placement issue. Okay, so let's just do this for right now as if we're only working with areas above the x-axis. Now, let me ask you guys a question. If this was 5 and this was 12, then how far is the distance between them? 7, exactly. Now let me ask you this. Excuse me. If we're going to cut this into, so if we wanted to find the distance between them, it would be 12 minus 5 or 7. And if I wanted to cut that into 2 rectangles, how big would they both be? How wide would they both be? If you wanted to cut this distance into 2, okay, so you would just take this and divide by the number of rectangles that you would want. Do you agree with that?
Yeah.
So the idea is, on your papers, you guys have a little thing right here that says, how big is delta x? And delta x is always going to be, take the endpoint on the right and subtract the endpoint on the left. So you have to first find the distance between the two, and then divide by n. That's going to be, remember the way we're doing this right now, each of the rectangles is going to be the same width. So they're all going to be exactly the same width, exactly the same width, exactly the same width, and then dot, 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 as many as we can fit in, or infinitely many. You get the idea? Okay. And we've referred to this little segment right here as delta x. And what we're saying is delta x can really be found by doing the distance between B and A, dividing by n the number of rectangles that you would do. You okay with that idea? Okay, over on the right-hand side, next to that, you guys see RHE. Let me see if I can make this make a teeny bit more sense than I did yesterday. Now that it's day 2, it may. When we want to try to find the right-hand rectangle, so here's the idea. Obviously, I want to find the area from A to B. I want you guys to take a look at the first little rectangle and go, the right-hand rectangle is the one that has the endpoint right here. Now, let's look at this x value right there. That x value is A plus 1 delta x. Would you agree with that? So if I want the y value there, I'd have to do f of that amount. Do you agree with that idea? That would be the height right here. So if I went over this way, it would be f of A plus only 1 delta x, because I went over 1 delta x. Do you follow that idea? Now if we went over to the next one, if we wanted to find this little height, we'd have to go over to this spot right here. That would be A plus 2 delta x. Do you guys agree with what I'm saying? This little spot right here would be A plus delta x again. That would be that point. And then to get that height right there, you guys would have f of A plus 2 delta x's. Is that making sense to you? Now, when we do this with the calculus, we don't use multiple delta x's. What we do is we use the b minus a over n. So your right-hand endpoint starts off with, I'll do this in black here, A plus, I mean, it is delta x, but it's b minus a. That's supposed to be b minus a over n. And then this thing over here says times I, because you need to know how many rectangles you're moving over. If we go over once, that would be I equals 1. If we go over twice, that would mean I equals 2. So we go over n times. Does that kind of make a little bit of sense? Just like I did this with like 1 delta x, and then this is 2 delta x's and 3 delta x's. Remember, this expression right here is the same as your delta x. Okay? So the big picture is trying to find the area of this. Now this is the first time we've actually done the notation that I've been talking to you about. If we want n rectangles to be infinitely many rectangles, then this is how we do it. On your paper, does it say equals or does it say approximately equal to? Does it say equal for area or approximately equal? Equal? Do me a little approximately equal here, because it's not exactly, right? It's going to be off just a tad, so approximately equal, and this is how we do it. Now, this does not mean that we're going to have to do limits out the yin-yang right now, but you remember the idea of limits a teeny bit? Possibly, you've heard it before, maybe last fall, not as long ago for you guys as it was for the other class. Now, on the sigma expression, you guys have a blank, and you've got the sigma expression, and you've got some spaces on the sigma expression. And the spaces on the sigma expression are asking you to fill them in. So what we always start with when we're doing these little rectangles would be I equals 1. Because we're talking about the first rectangle, and the second, and then the third, and the fourth. You with me there? And we want to do this from I equals 1 to n, either specified by the number of rectangles we have, or n's going to infinity. So kind of the street way of writing this would be going from I equals 1 to infinity. Do you know what I mean there? But this is the way we appropriately write it with calculus. And then this blank over here just needs to be the formula for how you find the area of each of the rectangles. And that's what we have right, where do I have that? I don't have it anywhere, but it's this. Remember, we need to know the height times the width of each of the rectangles. Now, when we do the height, it's normally f of the right-hand endpoint times delta x. That's it in general form. Agreed? But I want to write it in terms of what we have here. Your right-hand endpoint is this, right up there, and your delta x is this right over here. So if we want f of the right-hand endpoint, we're going to have f of a plus this right up here, plus b minus a over n times I. That's how we're going to find the height of each of the rectangles. That's the height of one rectangle. Now this says I because you're going to do it from the first rectangle when I is 1, plus you. Second rectangle when I is 2, third when I is 3. I got to show you. Probably times, then we need to do the width. And the width is typically delta x. Let me space this out so you guys can see. That's delta x. And the width is b minus a over n. And again, I'm getting that from the stuff we put up at the top. Okay? So this is like the big picture. This is what we're going to be using when we do these problems. And you're like, well, we haven't seen the problems yet. I understand that completely. You guys are paying attention. Not necessarily. Okay, so tap on the orange marker. Now, if you take a look at the next page in your notes, does it start with, up at the top, this means we are adding, and then it has some blanks, and blah, 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 and then it says let n equals 4, and then it does all this for an arbitrary number of rectangles, and all this kind of stuff. Do me a favor on your next page. We've already talked about all of this and what we've done yesterday and the day before and so far today. So this is how I want you to fill out page 3. Big old X. Because we've already put this together in what I've talked to you about. All you need at this point is the bottom line. This key picture right here, this is it. This is how we're going to find the area approximately underneath the curve. Just cross out page 3. That's how we're going to fill it out. You've already heard the theory behind it. You've gotten to the bottom of page 2. I probably ought to just wipe it out in this packet. and I just wasn't as organized as I thought I was. So wipe it out, that's sweet, you're like, yay, we have less to work on, awesome. Then you're like, I know, that was good, I like the yays. Now, then you get to the page where it says, Remon Day 1 examples. And we haven't done examples yet. And you're looking at these, they have graphs, you're like, okay, got that. And then there's this limit stuff, and this time we're not just setting these up, we're supposed to come up with answers. So let me do a little bit of review with you of some sigma formulas that we're going to need for this. I'm going to show you most of them. I say most of them because that's the plan. But not all of them, because there's one of these that we just don't need to do. If I were me, and I had taken a stack of papers for you guys and put them, there they are, right here for you guys. I did a really poor job of hole punching some of these today earlier. My apologies. So I'm gonna hole punch these on both sides so that if you're a binder kind of person, you guys can put yours in upside down, backwards. This is gonna just be a little brief summation review. If I say summation, do you know what I'm talking about? Adding a bunch of rectangles, adding a bunch of terms in a series. Now, a series in math is a list of terms that you're adding together and trying to get an answer. We're keeping Cole awake today. Look at it, yawn. Well, I shouldn't say yawn, David's in there. Now he's gonna start the yawn game.
No, don't do it, don't do it.
I know. Here we go. Take it away, David.
You didn't have to yawn, you were just opening your mouth, getting the power.
Yeah, but then he starts and then he really does yawn for real.
You say the word yawn,
Oh.
I know. Power of suggestion there. Okay. This one, I think it's easiest if you guys are able to follow along here and I don't have to keep writing these things down, because your paper that you have in front of you is exactly what we're going to go through. Okay? So, you have this summation review here. This is going to review sigma with you. Hold on a sec. Wait for this thing to turn on. We should be in good shape. This is where we need like commercial music. Not sung by me because you would run out of the room kicking and screaming. Okay. So, thank you. That's good. Thank you for helping me with that.
Why do I need my desk on here? Like, am I gonna get happy filled and I'm like incapacitated?
Maybe you knock your teeth out, and then you can come and do
Or
it.
get my teeth knocked out?
Ready?
Hey, maybe you
Okay.